Thanks, Susmita. It's like really a privilege to introduce the first speaker today, Arindam Khan, who is a faculty member at IISc. Uh, Arindam was my 1 year junior in Kharagpur, and I'm delighted to see his progress in the wonderful work he has been doing over the years. So, just to introduce Arindam did his PhD from Georgia Tech, and he has been working in mainly in theoretical computer science, but his work spans multiple areas of theoretical computer science. So he has been working in approximation algorithm, combinatorial optimization, online learning, online algorithms, and geometric algorithms, and many other areas. Okay, so his wonderful work has already been recognized with different awards and things. So I will just mention a few because the list is so long. It's He got the best paper award. He and his co-authors got the best paper award in International Symposium on Mathematical Foundations of Computer Science. In 2020, his work has appeared in Highlights of Algorithms. 2021, he got Pratiksha Trust Young Investigator Award, Google Explore CSR Award, and more recently, the Google India Research Award. Today, Arindam will be talking about his breakthrough result in uh, for approximating independent set in intersection graph of rectangles. So, Arindam, we are really looking forward to your talk.
Thanks a lot, Urijita, for such a kind introduction, and thanks a lot to the organizers for this invitation. Okay, so welcome everyone. So this talk is on approximation algorithms for maximum independent set of rectangles, and it's a joint work with 5 people: Waldo Galvez from TU Munich, Madhusudan Reddy, who was an undergrad at that time, third-year undergrad from IIT Kharagpur, and now he has started in CMU as a PhD student; Matthew Mary from University of Warsaw, Poland; Tobias Momke from Germany; and Andreas Wiese. He was in Chile that time, but now he has moved to Netherlands. So in this talk, it's a 2-hour talk. So first hour, today actually I'll focus on the background, and I'll talk about other problems also in this area. And maybe at the end, I'll start talking about technical details of our result, and tomorrow it will be more technical. And please feel free to stop me at any point. I want to keep this as interactive as possible. So if you have any question, please feel free to ask me, stop me at any point and ask the question. So let's start. So we have, as I said, the talk is on approximation algorithms for maximum independent set of rectangles. So first I'll talk about approximation algorithms, then rectangles, and then maximum independent set. So it might be, most of you already know about approximation, but for those of you who do not know, just to define, approximation algorithms are efficient algorithms that find near optimal solution. And it's a very classical area in theoretical computer science. There are multiple textbooks. For example, this Smoish and Williamson or Vazirani's textbook is there. And the talk that I will talk about, it mainly focuses on geometric approximation, which is an intersection of approximation algorithm and computational geometry. And for that, the textbook by Sariel Harpelez and other resources are there. So an algorithm for a so it's an optimization problem can be minimization or maximization. The problem I will talk are mostly maximization, but in some related problems, I'll talk about minimization as well. So for a minimization problem, an algorithm A is alpha approximation. And this is called absolute approximation as well, because there is a notion of asymptotic, which will come later. If AI, which is the value of the solution of algorithm on instance I, is within alpha times opti, where opti is the value of the solution, optimal solution on instance I. And for maximization problem, I define an algorithm is alpha approximation if opt I is less than equal to alpha times AI for all input instances I. So there is normally people measure the approximation ratio by the ratio of opt I by AI or opt I by AI. So people try to make alpha. So in this talk, actually, I focus on alpha more than 1. So the definition is slightly changed, and that's why I kept this definition, that opt-I for a maximization problem is anyway more than AI. So we want AI to be as close to opt-I. So I want it is less than equal to alpha times AI, and alpha should be as close to 1 as possible. And as I mentioned, this is called absolute approximation. There is another notion of asymptotic approximation. For minimization problem, that talks about the case when optimal solution is large. So this is the expression. So let me explain what is this saying. So just first focus on the things in under this curly bracket. This is saying, okay, we're looking at the ratio of AI and opti and the maximum ratio there, given that opti is equal to n. So given a particular value of opti, I'm looking at all instances for which we get this particular value of opti and looking at the worst case ratio of AI by opti. And then I look at the lim sup when n tends to infinity. So when n tends to infinity, what is the approximation guarantee that we get? So intuitively that says that if I have alpha asymptotic approximation, then let's say AI is less than equal to alpha times opti plus some small o of opt. So think of constant. If this kind of things happen, we call the algorithm to be alpha asymptotic approximation. Okay. So any questions so far about definition, because this is needed, the definition of approximation algorithm and so on.
Arindam, it like n tends to infinity, the value of opt tends to infinity here.
Yeah, so when n is not the number of items in this case, n is basically the value of optimal solution. So when opt tends to infinity, yeah, they're same. So opt equal to n. So when optimal value tends to infinity, what is the approximation ratio that you get? That is called asymptotic. In the asymptotic setting, what is the approximation ratio? The reason it is considering the asymptotic setting is sometimes for some pathological instances, you can have maybe opt equal to 1 or 2. And then algorithm perform very bad. You need maybe 2 when opt equal to 1. So you get ratio 2. But maybe for large values, you also get opt plus 1. So then the ratio is much better compared to factor 2. Okay. Now in this talk, I will talk a lot about petas. And there are several types of petas. So petas is polynomial time approximation scheme. And we call, for a problem, we call the problem is admitting a petas if for any constant epsilon, positive constant epsilon, there exists a polynomial time algorithm A epsilon such that A epsilon I is less than equal to 1 plus epsilon opti. And the runtime depends on epsilon. So it could be n to the power function of epsilon. Think of n to the power 1 by epsilon, something. So if epsilon is a constant, then it is a polynomial time, n to the power constant. And this is saying that for any epsilon, you can get this. So you can get as arbitrarily close to opt as possible, but the runtime will increase as you get more and more closer to opt. So this is called petas. Now there is a variant called epetas or efficient polynomial time approximation scheme. Then it is petas, but the runtime is slightly better. So now what you want the runtime to be order of function of epsilon times n to the power c. And here the exponent of n, the c, it is independent of epsilon. So think of an example of runtime, something like 1 by epsilon to the power 1 by epsilon times n to the power 100. That's a epetas kind of a runtime because the exponent is independent of epsilon. Then third one is called fully polynomial time approximation scheme or fpetas, when the runtime is polynomial in both n and 1 by epsilon. So think of 1 by epsilon square n cube, something like this. So epetas, fpetas, and petas. And there is complexity theoretic relationship. So if you know a problem is apx hard, then it will not imply a petas. If a problem is w1 hard, assuming opt is the parameter, then it implies no epetas. And if a problem is strongly NP hard, it implies no fpetas. Some more petas. So one is called asymptotic polynomial time approximation scheme. So it is petas, but in the asymptotic setting. So as I mentioned, the asymptotic ratio or approximation ratio becomes 1 plus epsilon. So this extra part, you can think of this as a small of opt as well. But for now, assume it's just constant. So it's a constant. So when opt is very large, opt tends to infinity, this constant is very small compared to opt. So you can ignore the constant and the ratio you get is actually 1 plus epsilon. Then there is something called quasi-polynomial time approximation scheme or QPetas. So here we get 1 plus epsilon approximation. But the runtime is quasi-polynomial. That is n to the power poly log n. So n to the power log n or n to the power log n square, something like that. And finally, there is something called pseudo-polynomial time approximation scheme or PPetas. This is again a petas, but not polynomial time runtime, but the runtime is pseudo-polynomial. So it's some n to the power constant, but n is the number of items and the numeric data that we have, it's polynomially bounded in n. So think of knapsack kind of problems. There's a numeric data, size of a knapsack or profit of a knapsack. That data, numeric data, it's polynomially bounded in n. So here I am assuming n to be the number of input items and the input, basically something like input. There is a question. So QPTAS runtime. Oh yes. So QPTAS also depends on epsilon. So I did not mention. It is basically n to the power log n to the power order 1 epsilon. So basically the constant that we have here, you can have it a function of epsilon. So for constant epsilon, it will become a constant. So QPTAS also has dependency on the epsilon. And the advantage of QPTAS is if you want to show some problem admits PTAS, then QPTAS kind of shows that it implies the problem is not APXR unless some complexity theoretic assumption like NP is subset of d time 2 to the power polylog n. So we kind of believe that if a problem admits QPTAS, it should also have PTAS. So to show it's not algorithmic, but kind of you believe if a problem admits QPTAS, you should get a PTAS. So any questions so far regarding the definition of PTAS, QPTAS, etc.? Okay. So now we'll talk about the second term, rectangles. So I know everyone knows rectangle, and in fact we love rectangles. So be it as financial K matter or
Arindam?
Yes, please.
Can you just go back to the previous slide once? Sorry.
Yes.
It implies it's not APX hard. Okay. Yeah, fine. Got it.
So basically, we expect it to have a PTAS.
Yeah.
So yeah, we love rectangles from money to, let's say, flag to cricket pitch, etc. In fact, I mean, even in art, people like rectangles a lot. So some modern art examples are like this. So this figure is, its name is Suprematist Composition. This one is Blackfire, and they are sold like $90 million or something, the price. So even in arts, people like rectangles a lot. So in fact, people sometimes, so when scientists look for biomarkers or existence of life in exoplanets, they normally look for this oxygen level, because normally oxygen is a highly reactive element, and if you have oxygen in a planet, then that means there is something which is producing oxygen. There is some life there. But I'll say maybe rectangle is one of the biomarkers that we should look for, because you'll not find rectangle in nature, but for man-made structures, probably this is the most frequently occurring structure that we will see. So that's the reason like rectangles are so well studied even in mathematics and so on. So if you look at classical people in discrete math and theoretical computer science, many of them have studied this kind of rectangles or packing problems. So by packing problems, I mean placement of objects non-overlappingly under some constraints. I will define more formally later, but like Paul Edosh or Ron Graham, like Edosh started this area of probabilistic method, and Graham was the first person to give approximation algorithm, this scheduling problem, and even modern day greats like Terence Rao. All of these people are looking at this kind of rectangle packing, square packing kind of problem. There are dedicated websites which talks about packing things. For example, there is a website called Eric's Packing Center. If you search, you will go to this website. And this is only 5 examples I have here, but if you go to the website, there are I think 30 or 40 examples. So all types of permutation combination, triangles in squares packing, rectangles in rectangles, squares in squares, squares in rectangles, and so on. So all these different types of variants you have, and what is known for each of these cases, those things are there. So it's a very well studied area. So once I was watching a video by Eric Diman, and he mentioned one thing, that I think packing problems are appealing to mathematicians and computer scientists because they seem very simple, and the simplicity and elegance is kind of attracting many people. So you just need to place some items into container or some boxes and so on. but yet they tend to be extremely complicated to actually solve. So the elegance is the problem definition, but to solve them, actually, you need a lot of sophisticated tools. So we're done with rectangles, and now finally, I will start with maximum independent set. So independent set is a very classical problem, and independent set is a set of vertices in a graph such that no two vertices are adjacent. So for example, in this graph, the star graph, I can take either only the center vertex or the leaf vertices. Both are in independent sets. Similarly, we can take this hypercube graph, and there are many different independent sets. So in case of maximum independent set or MIS, the goal is to find maximum sized independent set, because you can have different size independent set, and in this case, this will be the maximum size independent set. In the other graph, either this size 4 or this size 4, there are these two sets which correspond to maximum size independent set. So red vertices are the independent set in this figure. And this is a classical NP-hard problem. And one can see it's easy to get a trivial n approximation, because you can take just a isolated vertex. So n is number of vertices in the graph. So if you take just one vertex, it has no edges with any other vertices. So that means it's an independent set, a single vertex. And in the worst case, you can have it's a completely disconnected graph, and there are n vertices. So you can have n vertex in the maximum independent set. So at least you are getting one, so you get n approximation. That is extremely trivial. But it turns out that is okay. And then you can slightly improve it further, and you can get something like order n by log cube n. So this tilde notation is hiding some log n factor. But as you see, it's slightly better than n, but not a lot better. And it turns out you cannot really do much better. So there's a classical result by Hastad, which showed it's NP-hard to get even n to the power 1 minus epsilon approximation. Even n to the power 0.9999 is not possible if you assume NP is not subset of ZPP. There is slight improvement here in the hardness, but still, I mean, you see, it's still, you're nowhere close to getting a good approximation factor. So that's the present status for general maximum independent set problem. But we'll look at special graph classes for which this is easier to solve. So any question till now? Yeah, I said, please stop me at any point of time, because we have 1 hour time today. I need it to be interactive, and yeah, you can ask question anytime. Okay. So now we'll talk about this geometric intersection graph. It's a special type of graph. And here the nodes are corresponding to some geometric objects. You can think of polygons, spheres, disk, rectangle, etc. And if two objects overlap, then there's an edge between them. So think of a setting. It is an office space. It's an example I'm giving. Let's say COVID situation we have. So in this office cubicles, if someone sits, there is a radius of maybe 5 meters or 3 meters within which you don't want to enter, because then there is a chance of contamination. So each of these chairs or cubicles, they are defining some kind of a disk region, and maybe it can have different disk sizes depending on the proximity to window or AC, etc. And then you can define this as an intersection graph. So objects are now disks, and if two disks intersect, you create an edge between them. So the graph will look like this. For example, these two disks, they are intersecting, so I create an edge between them. There are nodes corresponding to these two vertices. Similarly, for this, I create one node, and these two are intersecting, so I create an edge between them. So that's the way we create the graph. So it has both geometric interpretation as well as a graphical interpretation. And the goal is to find the maximum independent set in this geometric intersection graph. So from graph theoretic point of view, if you look at the graph, this is an independent set because none of the vertices are sharing any edge. Okay. These red vertices are defining an independent set. And in terms of geometric viewpoint, this is saying that the objects are non-overlapping. So there is a graphical viewpoint from independent set, and from geometric viewpoint, it says that objects are non-overlapping. Yeah, so this area actually is quite popular. So I was just few days back, I was just looking at DVLP, and I found in India in last 10 years, probably there are 50 researchers who have published at least one paper related to this area, geometric intersection graph. So either in geometry or approximation or structural graph theory and so on. So it's a very popular object, at least in India. So recent trends of algorithms in India, at least it has been a recent trend to work on this area. So before going to complicated objects, I will start with the simple object of intervals. So think of the case when the nodes are corresponding to intervals. So there is an edge between two intervals if they are overlapping, and the goal is to find maximum independent set in this graph. And geometric viewpoint is finding the maximum cardinality non-overlapping intervals. Now this is so in this, for example, in this example, these are the intervals. So I drew it like a two-dimensional thing, but actually just to show the intervals. The first interval is between 0 to 3, second is between 1 to 4, and so on. And I can create nodes corresponding to each of this. So maybe this is the first one and second one. So I can create first node and second node. And if they're intersecting here in this region, so there is an edge between them. That's the way we create the graph. Now, this problem is solvable in polynomial time. So anyone remembers from undergrad algorithms, how do you solve these problems? Solve this problem?
The algorithm.
Yeah, so greedy. So greedy says earliest finish time. So basically what you do, you start from the left, and the first job that finishes, you take it, and then remove all the other jobs that's overlapping with this job. Then again, you continue, and the second job that finishes, you take it. And then again, you delete all the other intersecting job, and then you continue. The third job that finishes, you take it, and you delete the rest and continue. And then that will give you the set of intervals. And in this graph, you can see these three nodes are corresponding to the set of intervals. So greedy works in the unweighted case. Now, if we go to the weighted case, you can show the greedy does not work. You can probably take maybe a very high weight for this particular job that you removed and very smaller weight for this one. And then if you remove this job, you're already gone. So greedy will not work, but dynamic program works. So weighted case, how do you solve using dynamic program? So think of again the case when we have these intervals, and now they have weights 3, 3, 5, and so on. And how do you solve it? So here the DP idea works on divide and conquer. So there are two types of DPs, but I will focus on the DP based on divide and conquer. So what we'll do is we can look at all these points, and then I can divide this region into two regions, left and right. So whatever interval is cutting this straight line, I delete it, and the remaining portion I solve recursively, the left part and right part. So I can have many positions to consider. Maybe this one is one position, the second one could be another position, third one could be another position. And in this case, actually, I will delete both this and this because both are cut, and so on. So what DP does is it tries out all possible such cuts. Now, how many possible cutting points are interesting? So it's only interesting to consider the left endpoint and right endpoint of these intervals. So there are n intervals, so there are 2n number of endpoints. You can actually only consider these 2n possible cuts, and then look at the DP table for the left solution for the left portion and solution for the right portion, and then patch and select the best solution among all of this. And that will already give you the optimal solution. So just think for 2 minutes maybe later, and you will find out why this DP works. So our algorithm, finally, the rectangle algorithm will be a generalization of this idea only. So I will again try to find some cuts and solve these problems recursively, the smaller problems recursively. Okay. Any question regarding this part? Okay. So now,
Arindam, just to get some more intuition. So essentially you are guessing the cut, right?
Right.
I mean, you cannot just cut at the middle because that might be the wrong cut. So you are trying to guess the correct cut such that you can do the patching. That's what your DP will figure out, right?
yes. So the point is, the guessing is not a difficult job because there are only 2n number of cuts that
Yeah.
So you just try out all possible cuts, and DP table will still have polynomial size.
Right. But each level has n choices, right?
Okay, so let me write the DP then. So let's say the DP x1, x2, it contains the optimal solution in the range x1, x2. So let's say starting position was n and ending position is 2n. So I want to compute DP of 1, 2n. That is the final thing I want. And what I do is I look at the maximum over all I, and then I look at the solution of dp of 1, x plus dp of x, 2n.
I see.
Not oh, it's I basically. 1, I and 1, so I is basically going from 1 to 2n.
Yeah.
And then I look into it, and when I look at this line I delete all this, I remove all the intervals that are intersecting this ith cut, and then I just look into the dp table, and you can construct it bottom up, this dp table.
Right. Yeah. Okay, fine. Thanks. Yeah.
Okay. So now we go to slightly complicated objects when you have squares. It's again quite simple. Actually, a simple greedy algorithm will give you 4 approximations. So normally it's a homework in approximation algorithm or computational geometry course. And the algorithm is as follows: that you sort the squares according to their sizes, and then select the smallest square, and then remove all the squares intersecting it, and continue. And that already gives you a 4 approximation. And you can explain it in terms of relating something called piercing number with independence number, and then you can chart the corners of the rectangles for each of these points in each of the square in optimal solution. And this idea of squares can also be extended to other objects like disks and fat objects. By fat object, I mean object something like this. Like it's a convex object, and if I look at the largest disk inscribing this object and smallest disk circumscribing the object, this ratio is constant. That's why it's kind of fat. So if I have an object like this, it is not fat because the ratio is really large, small and large, whereas a fat object will have square or disk or things which looks kind of not too thin. They are called fat objects. So most of these approaches actually extend to fat objects. And the reason maximum independence had become an important problem because it developed a lot of techniques for these problems, and those were useful for many other problems. For example, first Hobsbawm and Maas gave Peters for unit squares using a technique called shifted grid, which has been very useful in many problems. Then for arbitrary squares, even with weights, there are techniques called shifted hierarchical decomposition, which gave Peters, and then Timothy Chan also gave quad-tree-based algorithm, which gave Peters. And then there are geometric separator theorem similar to planar separator theorem, which again gave Peters for arbitrary squares. One can use local search algorithm for arbitrary squares and so on. So a lot of techniques developed around this area, and it was useful for many other problems as well: geometric set cover, geometric fitting set, and so on. So now we'll talk about rectangle. So one thing is, for rectangle, many of these techniques don't extend because rectangle is not a fat object. It can be very skewed. The ratio between the width and height can be arbitrarily bad. So things like shifted grid or hierarchical decomposition or local search don't work, as we know, for rectangles. So we'll see only there are 2 main techniques which will work for rectangles. One is linear program, other one is dynamic program or separator theorem based dynamic program. So those of you who joined late, you can actually start from here. I will again define the problem that we are studying. So we're studying maximum independence of rectangles problem, and in short, I will call it MISR. And in this case, we are given a set of n axis parallel input rectangles. We are assuming axis parallel rectangles. There is one question: do all of these works deal with squares or rectangles in 1 or 2 dimensions? No, most of these works that I talked about for squares, they can be extended to d-dimensional hypercubes as well. So if it is d-dimensional fat objects, it also extends. So think of cubes or 4-dimensional objects and other things are not really practical, but they have some application in database and so on. So they still work in those kind of objects. So a set of n axis parallel input rectangles. We are assuming axis parallel property here, and the goal is to find a set of non-overlapping rectangles of maximum coordinality. So in this example, I have 5 rectangles, and I can create 5 or 6, maybe 6 rectangles, and I can create corresponding graph as well. And the goal is to find independence in the graph or the maximum set of non-overlapping rectangle for rectangles. And this has many applications. For example, in map labeling, data mining, resource allocation. Think of a problem where this one dimension is like bandwidth, and other dimension is time duration. So now these job requests are asking for some amount of bandwidth for some time duration. So it's basically rectangles that you are getting, and your goal is to allocate maximum number of such rectangles. So, okay, practical motivation is there, but as it's a talk in theory CS, why it's an important problem in theory CS? One of the reasons it's important because it has a lot of connections with other problems. But any questions so far about the problem? Okay. So theoretical important ways. So there are this class of problems which I call bin packing type, and other one is knapsack type. And we're looking at packing problems. So our goal is to find some axis aligned non-overlapping placement. For now, as you only we're talking about rectangles. And depending on the rectangle's movement, you can define different problems. So in some problems, you can take a rectangle like this, and maybe you can move it anywhere, like vertically or horizontally. So that we'll see bin packing and knapsack as those kind of problems. In some problems, we'll only move vertically, but not horizontally. And sometimes we'll not allow any movement. So one question, can axis parallel constraint be waived? So I will talk about this later, but it seems it's very hard. So for example, if you just take line segments, one can, so I will talk about this later, but it's quite hard. For example, if you just take line segments, what we know is a simple two approximation algorithm. If you have axis parallel line segments, but which is a special case of axis parallel rectangles. But if you even take arbitrary line segment with any orientation, then the based on approximation is n to the power epsilon. So from 2, you go to n to the power epsilon. Even a poly n is not known. Even a poly log n is not known. So the reason is, if you have this arbitrary orientation, if you don't have the axis parallel property, then you can have much more complicated interaction between the objects, which is difficult to handle. So that's why people focus on axis parallel. So many of this can be extended to the setting where instead of only 2 orientation, so in axis parallel you have kind of 2 orientation basically. So the largest side of a rectangle is either vertical or horizontal. You can still extend to constant types of orientation, but extending it to arbitrary types of orientation is hard. It's difficult. Another reason people study axis parallel setting is because of the practical importance. For example, the motivation of IISc came from this bandwidth allocation kind of problem, and there it's exactly axis parallel. There are 2 resources, and basically the width is telling how much amount of resources it requires in one dimension, and the height is telling how much of the resources it requires in the other dimension. So that's why axis parallel is very well studied, and also in practice, many of these problems are coming from cutting problems as well, where you have some objects and you have to cut through machines. And in practical industry, people have this axis parallel cutting mechanism because it's easy to implement. So that's the reason axis parallel problems are more well studied. And also, if we don't have this constraint, it's very difficult. So at the end of the talk, I'll talk about the open problem. If we don't have this constraint, can we get even a polylog n approximation, log n to the 1000 or billion, if it's possible. But for rectangles, we'll show you can have much better ratio. You'll have actually a 2 plus epsilon approximation when you have axis parallel rectangles. Okay. So now let me talk about this slide and different problems with which IISc has connection. So in bin packing type problem, we have some rectangles. So in both these problems, we have some rectangles and we're going to pack them. And by packing, I mean it's a axis aligned non-overlapping placement. In bin packing problem, the goal is to pack all rectangles into minimum number of square bins. In knapsack problems, the goal is to pack maximum profit subset of rectangles into 1 unit square knapsack. So it's just like knapsack and bin packing classical problems, but instead of just unit bin, now we have unit square bin. Now, if you think of the case of 2-dimensional bin packing, then you have some rectangles you want to pack them into unit square bins, but you can place rectangles anywhere you want. You can move it vertically or horizontally. And in this case, the base known approximation is 1.405, and we know the problem does not admit any epitath, asymptotic polynomial time approximation. For two-dimensional knapsack, the base known approximation, it's again similar, but you want to pack a subset of rectangles. You can move it anywhere and pack it into the knapsack. The base known approximation is 1.89, and we expect a epitath in this case. But yeah, so this is the two problems we have, and you can think, I mean, these are basically generalization of bin packing and knapsack. If you think of all rectangles have same height, exactly height equal to 1, then this is just this reduces to one-dimensional bin packing or one-dimensional knapsack. Then the other condition problem says that okay, now the rectangles are fixed, their horizontal locations are fixed, but you can move them vertically, and then it's called unsplittable flow problem or storage allocation problem or round SAP problem, round UFP problem. So the problem is as follows. Let me talk about storage allocation or unsplittable flow problem. So it's a graph problem again. You have some path. Okay. It's not appearing for some reason. And then you have some jobs. And so these paths are saying, okay, maybe some time intervals and which job is from what time to what time. We are given some jobs. And there is some profile, some capacity profile. So you want to schedule these jobs under this capacity profile such that, I mean, in that case, you can place the jobs, you can place it here or here or here, it's fine. So you can move it vertically, but the horizontal position is fixed. You cannot really move it. And the goal is to find a maximum profit subset of jobs, which you can fit like this. So it's a problem known as a storage allocation problem. And in unsplittable flow problem, it is similar, but you can also slice the rectangles. And you can, so there the goal is to, if you look at one particular edge, total amount of resource requirement by all the jobs placed in that edge should be at most the capacity of that edge. And this is again a very classical problem. I mean, in UFP alone, I think there are more than 20-35 papers in SODA. And very recently, this year only, there is a PTAS for this problem. And for storage allocation problem of SAP, there is a 1.69. So there is two variants. One is called uniform, where the capacity profile is uniform throughout the edges. So it's basically a rectangle type of object. But in the other case, you can have general profile, arbitrarily shaped profile on top. So for SAP, the best known result for general profile is 2 plus epsilon, and for uniform capacity, 1.69 is the 96 is the best known. And then there is a similar variant called round SAP or round UFP, where you want to find this kind of UFP packing of all jobs, but into minimum number of bins. And bins are this capacity profiles. And for this, there is a 2 plus epsilon approximation known, and there is the order log n approximation known for the general profile. And if you look at MISR, it is again a special case of this kind of problems where the rectangles are not allowed to be moved. So they are fixed. And now you want to find minimum number of bins where you can pack all the rectangles without any overlap. So that is rectangle coloring problem. In other words, you want to color the rectangle into minimum number of classes such that each color class are disjoint. And in the MWISR or weighted version of MISR, the goal is to find maximum profit subset of rectangles into one knapsack such that none of them are overlapping. So in this packing, the rectangles are fixed, so you cannot move them. And it turns out the technique for one problem is kind of transferable to other problems in this area. For example, the log n approximation for MWISR, those kind of approaches have been used in the algorithm for round UFP or round SAP. Similarly, for even UFP PTAS algorithm, before that there is some other work which also use some special class of MISR instances to obtain improved approximation for UFP. Even for two-dimensional knapsack or two-dimensional strip packing, other packing problems, there's a technique for MISR which is called corridor decomposition, which was used to give improved approximation for these problems. And in turn, these two-dimensional knapsack algorithms were used to give better algorithms for two-dimensional bin packing and so on. So there's a connection between all these problems, and that made this MISR problem to be very important. So it has connection with many problems: two-dimensional bin packing, knapsack, strip packing, UFP, SAP, round UFP, round SAP, rectangle coloring, geometric set cover, geometric heating set. For example, some geometric separator-based approach for MISR was used to give improved approximation for geometric set cover problem for some particular objects. So that's one of the reasons MISR was so important. The techniques developed for MISR was useful for many other problems. And also it has deep connections with other areas like structural graph theory or discrete or commutative geometry. So I'll talk about this later, not today, but there is something called chromatic number and clique number of chi-bounded graphs. So chi-bounded graph means this ratio of chromatic number and clique number are bounded. And one can show that there is a linear program for MISR. Whatever integrality gap of the linear program is, that gives you a bound on this chromatic number and clique number ratio. So that gives you some structured properties for this structural graph theory. Similarly, we'll come across this Park-Tardos conjecture, which is not dealing with really algorithms, but it's more a combinatorial question, and it has connections. So if you solve Park-Tardos conjecture, it will imply an approximation algorithm for MISR and so on. So that's the reason MISR is theoretically so important. So any question regarding these problems or MISR till now? Okay. So now let's talk about MISR results. Oh, it's already almost 45 minutes, I guess. So the work of Khanna, there are multiple algorithms, log n algorithms known for the problem, 3-4 algorithms. And then actually there was improvement and people showed you can actually get as close to log n as possible. This constant before log n can be made as small as possible. Then if you have Q to be the clique size, then one can show 4Q, you can get an approximation of 4Q. Then Marx showed that even for squares, the problem is W1 hard. So we don't expect a epitas for this problem. And then Chalamsuk and Chuzai showed order log n algorithm using linear program. And we'll see this linear program later, maybe tomorrow. And then Arindam and Vise showed that this problem admits a Q-pitas in n to the power poly log n by epsilon time. There was further improvement by Chuzai and Na, and it was shown that you can actually get even better than Q-pitas. You can get poly log n time algorithm, n to the power poly log n time 1 per epsilon approximation. So people expect it should have a pitas because we have a Q-pitas for the problem. But till recently, log n was the best known algorithm. Even a constant was not. So recent breakthrough by Mitchell first gave a 10 approximation. And it was a very surprising result. And the analysis was based on a lot of case analysis. So total 60 cases were there with some example of the cases. And it turns out, somehow it started with each of the cases and it worked out. So it was like a thriller. But finally all 60 cases were fine. And you can get it done. So the question was, can we get improved approximation, better runtime, and a simpler analysis, which does not go via so many case analysis. So what we showed is a polynomial time 2 plus epsilon approximation. So earlier there was a 3 approximation which was published in SODA this year, but then there was an improvement subsequently, which was 2 plus epsilon approximation. And the high level idea is what we do is we show existence of a good structured solution. Now, in case of MISR, for example, the candidate solution, the candidate independent set solutions can be huge. You can have exponential number of possible solutions. All subsets of n items could be possible candidate. So that's exponential. So that's hard to deal with. So what we need is we want to get some kind of structured solution, which is small in size, maybe n square or n cube or some polynomial in size. And this structured solution I can use as a good approximation of the candidate solution space C. So if I take any independent set in this set of candidate solution, then I can get a structured solution which is a subset of this independent set, but it is close enough. It's within alpha factor. So if I have this property, then what we'll do is we can we'll write a DP which finds the best structured solution. And structured solution, there are only polynomial number of candidates. So it can find the best structured solution. And then best structured solution is an alpha approximation of the candidate solution. So I'll get a good approximation of the original independent set. So the difficulty, so I'll show the DP-based algorithm, but it's quite simple. It's just extension of the previous DP-based algorithm that we talked about in the interval case. But that's quite simple. But the main difficulty is showing that, okay, how can you ensure you'll get a good structured solution? How do you prove that there is a good structured solution, and how do you find it? So even this good structured solution, existence of this may not be algorithmic. You can just show it existentially. There exists some solution because the DP will find it algorithmically. And it's also interesting because it's kind of tight what you are getting, is 2 plus epsilon, because even for line segments, the best known result is 2 approximation only. So think of axis parallel line segments and they're overlapping. So it's basically interval kind of setting, but now instead of only one direction, you can have both directions. So what you can do, how do you get a simple 2 approximation? You just take either vertical intervals or you take only horizontal intervals and then run the previous DP, for example. Then, or even the greedy algorithm in unweighted setting. That will already give you an optimal solution, and then you return the best of these two. That is giving you a 2 approximation. So even for axis parallel line segment, that is the best one, factor 2. And rectangle is much more complicated because much more complicated intersections can come in rectangles. And there we are getting 2 plus epsilon. So I believe to get beyond this, we need significantly new techniques now. So now I will go to the technical details, but it's maybe how much time do I have? 5 minutes, 10 minutes, or?
No, I think you have more than 10 minutes. It started at like 5 minutes past 10.
Okay, so around 11:05.
11:05 for sure.
Okay. So there is a question. Can you explain step 1 again? Yeah. So it's an NP-hard problem. The difficulty is because there are exponential number of possible candidate solutions. If you have n rectangles, possible number of candidate solution independent set could be any subset of this n elements. That's kind of exponential in nature. And if you want to go through all these solutions, that's too bad. You cannot do that. So what we want is, instead of so many candidate solutions, can we get a small sized, polynomial sized set of solution S, which is a good approximation. That means, let's say I have, S has polynomial number of candidate solutions, let's say n to the power 1000 or something. So if I have some independent solution which looks like this, okay, this is not independent actually, so maybe it looks like this. Maybe I can have a solution present in S which is very similar to this. Maybe I don't have this one, but I still have this two. So it's a good approximation, a subset of I, and it's within alpha factor. So maybe if I was 3 in this case, I prime is 2. So within 2 by 3 factor. So if I ensure S to have this property, that for any candidate solution, I can have a structured solution in S, which is close to the value of the independent set, then I'm done, because I can show there's a dynamic program which can find the best structured solution in S. And intuitively that is happening because the size of S is small. It's in polynomial. It's polynomial size. So DP intuitively can search over all these polynomial candidates in S and find the best solution. And that will give you the best structured solution. And as we know that if I take the optimal solution, that's also, there is a structured solution with an alpha factor of that, and we are returning the best structured solution. So at least it's better than that as well. So we are getting alpha approximation for the optimal solution. Okay, so now I have 10 minutes. I will not go over the technical part in detail. Maybe I will talk about guillotine cuts, one object, and tomorrow I will talk more about the algorithm for myself. So I talked about the structured solution, but what do I mean by structured solution? So let me give one example, and that will motivate the next step. So the structured solution we'll talk about is called guillotine cuts. Now, guillotine cuts, it's an end-to-end cut along a straight line, which divides a rectangular piece into two smaller pieces. So when I talk about guillotine cuts, now it is not an MISR setting. It's an independent problem I'm talking about. And now we have some non-overlapping rectangles which are inscribed on some piece. And I want to separate them using this kind of guillotine cuts, which are end-to-end cuts along a straight line. And it's practically very relevant, and in cutting stock kind of problems this is studied. So you want to cut out some required geometric objects from some large source material like glass, rubber, metal, or cloth. So you think of these rectangular objects as some kind of pattern that you need for your purpose, but you want to cut them. And the cutting machines only can cut straight line way. You cannot really bend, because bending it's problematic in many of these cutting problems. And it's also easy to program this kind of guillotine. So there is column generation technique which is used in programming this. So this guillotine cuts was studied from 1970s by Gilmore Gomodi in the context of cutting stock. And because of it has lower cost in this cutting industry and simple usability. Now, what is guillotine cut? So we want this end-to-end cut, and we want a series of guillotine cuts, and each cut will separate a subpiece into two new subpieces. Like in this case, the original piece was P, and this cut is dividing into two regions, P1 and P2. And then once you have these regions, this P2, I can again cut it like this, an end-to-end cut, another guillotine cut, and then I can have another guillotine cut here, which cuts P1 and continue. Now note that after I cut these objects, then they're independent, these two pieces, and I can cut them again differently. So the second level, the first level cut was this. The second level cuts may not be next to each other. I may not be continuous. I mean, one can be here, other can be here. It may not be like this. So I just want end-to-end on the smaller subpiece, not the entire piece. And it has connection with other packing problems. So, for example, bin packing, knapsack, strip packing, these are all studied under guillotine constraints. And for bin packing, there is a AP task. For 2D knapsack, there is a PP task. For 2D strip packing, there is also a PP task, and there is a tight absolute approximation guarantee. Okay. So this cutting sequence you can think of as a binary tree, where each node corresponds to some rectangular region, and each non-leaf node contains two children, which are obtained by this cut. So think of this previous pattern. So this was the initial object, and I cut like this. So I get two smaller subpieces. Then again, I cut like this. I get two smaller subpieces and continue. And at the end, the leaf contains only one rectangle in per piece. So then we call these leaf pieces are separable. I can cut out these leaf pieces. Now, we call a rectangle is extracted if it is not killed or crossed by any of the cuts, and at the end, it is the only rectangle in its subpiece. So, in this example, when I have this cut, I kill this rectangle to R2 because it's passing through R2. I cannot really separate out R2. And then I have the sequence, maybe I cut like this, and then this. And then if you see, all these rectangles are in one, are the only rectangle in its subpiece. So all rectangles except R2 are extracted by this guillotine cutting sequence. So given configuration is guillotine separable if all rectangles can be extracted using some cutting sequence. So this example I said, it's only showing one particular cutting sequence. It's not showing that it is not possible to do for any cutting sequence, but one can prove formally there are instances like this for which you cannot separate out all rectangles using a sequence of guillotine cuts. So for example, if you have this 4 pinwheel kind of a structure, whatever way you cut end to end, it has to cross one of the rectangles. You cannot extract 4 rectangles. At most, you can extract 3 rectangles. So then the question is, can we separate out at least a constant fraction of rectangles? So if you have n rectangles, can we get, let's say, n to the power n by 10 or n by 15? And it seems, yeah, it should be. And there's a conjecture by Park and Tardos, almost 22 years old, which they conjecture to be true. And it remained a big open question in this area because it has connection with other problems as well. We'll see the connection of this problem with MISR as well. So what is known for now is in this kind of a instance where it's basically coming from the previous instance only, but it's more square-like objects. If you're given n rectangles, then in this instance, you can show that you cannot separate out more than n by 2 rectangles using a sequence of guillotine cuts. So there is a factor 2 loss that will happen. On the other hand, the best known algorithm or even existential result shows that you can always separate out n by log n plus 1. Actually, it's order log n, I can say. A slight improvement is there. Rectangles using a sequence of guillotine cuts. So there's a huge gap. I mean, the conjecture is it's a constant. In fact, 2 is the conjecture that you can always separate out n by 2 rectangles, but we have n by log n. So 2 and log n. There are this huge gap, but nothing is known. So let me, okay, how much time do I have? Maybe at 3-4 minutes. I'll just briefly tell you the proof of n log n plus 1, and then tomorrow we can resume. So one observation you have is if all rectangles intersect a straight line, then they are guillotine separable. So this red line, it's crossing all the rectangles, and then I can separate out all the rectangles by the second stage of guillotine cuts like this. You can also extend it to say that, okay, if all rectangles intersect a T like this, so T can be like this or even this, depending on the arms are 0 or not. So if they intersect all rectangles intersect some T, then they are also guillotine separable. And using this property, we can have log n plus 1. There is a question. Either aim to find the location of independent set of rectangles and then separate out. Then we can use trapezoidal map. Yeah, actually, the locations are easy to find. There are only 2n locations. I mean, I will show, but I mean, you have n rectangles. So independent sets, you can stretch things, and the only interesting regions which are interesting are basically the corner points. Other points are not so interesting, and there are only 4n square corner points. So it's not the location of independent rectangles, but exactly find out what are the rectangles. That is the problem. So location is fine. The DP will find all the possible locations and then find it out. But then the point is, what is the best independent set? That we don't know. Okay, so yeah, so we can assume the rectangles are embedded in some 2n cross 2n grid with integral corners, because I can always consider the endpoints of the rectangles, and there are n rectangles, 2n endpoints on each of the dimensions, and then just make this non-uniform grid to a uniform grid. So then what I'll do is I'll create. So do I have 2 more minutes, Arijita? Or okay. So then what I do is I create this log n number of levels. So what I start with is this 0, this is 2n. At level, I look at the this width n, and I create this red pole, and then I look at n by 2 and 3n by 2, and I create this green pole and continue. So there are total log of 2n or log n plus 1 levels, and that will decompose this plane. And what I'll define is for a rectangle, the smallest level which is intersecting the rectangle, I define it to be the pole. So in this case, red rectangles are the level 1 rectangles because it's intersecting this red line. Then the green one is level 2. So the red one is already intersecting level 1, so it is getting already level 1. So though it is intersecting level 2 as well, I will assign it to the smallest level. So this way, I can partition this n rectangles into log n number of color classes. And then I claim each of these color classes are guillotine separable. So think of some color class like gray. So what I can do is I can take all the previous levels, and let's say they are red and green levels. They are partitioning the rectangles into several regions. And then if I look at any of the inner regions, then these rectangles are intersecting a single line. So I already proved if all rectangles intersect single line, I can separate them using guillotine cuts. So each of these color classes can be separated by guillotine cut, and that is giving you a separation of n by log n plus 1. And what one can show, you can slightly improve it to something like log n plus 2 base 3 using the property of t cuts. Then the question was, can we improve this further if you use more complicated guillotine cuts? And we showed it's not true. But I mean, till now we talked about guillotine cuts and showed this result. Now, what turns out there is a connection between this guillotine cut objects and MISR. And maybe today I don't have time to go over this. So we can show that whatever, if you show that given n non-overlapping rectangle, I can always separate out n by alpha fraction of the rectangles by guillotine cuts, then that will imply an alpha approximation for MISR. That is the connection. And yeah, I don't know. It will take 5 minutes to explain this, I guess. So maybe it's better to stop today, or yeah, maybe tomorrow we can continue from here.
Yeah, it's better we do it tomorrow.
Yeah.
Thanks, Arindam, for the very nice talk. So, any questions?
So just to relate to the DP approach, the divide and conquer DP approach you talked about for the interval thing, right? So this cut, they were also kind of the guillotine cuts, right? I mean, so okay, so that's the intuition that you will.
So I mean, there you don't even need cuts; you need points basically. Points. Sure. Now you have guillotine cuts extension. Now we'll see that okay. I mean, the conjecture is also equal to 2. So we should get a 2 approximation if we prove this conjecture.
Sure.
But the hardness is in the analysis. How do you prove this? So it seems that if we have these guillotine cuts, we don't have too much power. So what in the next lecture, what I'll show is you can have bends here. Instead of one guillotine cut, now you can have more and more bends. And the bends can avoid cutting more rectangles. And finally, we'll use that property to show this 2 plus epsilon approximation. So there are 2 questions. One is, do horizontal cuts are always vertical or horizontal lines, or bends possible? So yeah, by definition, guillotine cuts are end-to-end horizontal or vertical cut, and they're axis parallel. But you can also have non-axis parallel cuts as well in guillotine cuts. But in axis parallel rectangles, actually those will not help. You can show that for axis parallel rectangles, whatever you can do with axis parallel guillotine cuts, you can do with arbitrary guillotine cuts as well. But bends also will do in the next part. Instead of cutting like one straight line, we can have some axis aligned set of line segments like this, which will have the cut. So like instead of this kind of a guillotine cut, we'll have bends, and that will help us later. And does it help if all the rectangles and squares are of the same dimension? So what do we mean by dimension? You are saying the ratios of width and height are similar?
So assume lengths are same.
Yeah, then actually
all of them are of length 1. Okay.
All are of, yeah, I mean actually both the cases can be solved. There are 2 cases. One is when, so for square case actually we have proved this conjecture. So for squares we showed around 60 or something. I forgot the exact ratio, but some constant. This conjecture is true. So given embedding of n non-overlapping squares, you can always find n by let's say 81 fraction of squares which are separable by guillotine cuts. For squares, it is true. But for rectangles also, if you have same dimensions, so if the ratio of width and height is similar for all rectangles, then what you can do is you can stretch things and make them square-like objects. So instead of square, I can say if the width by height ratio is constant, they're like fat objects. So they can also be handled by this approach. Or if all the rectangles have same width or same length or almost same width or same length, that also can be handled. Those are special cases which can be handled. But in general rectangles, you can have arbitrary ratios, which creates the problem.
Okay, any more questions? There's another question.
Okay, why cannot we use arbitrary square algorithm for arbitrary line segments to get pitas? I guess we can translate a line segment in a square. So for arbitrary line segments, you mean even for axis parallel, let's say arbitrary is much more harder. You have any orientation, but even if you take, let's say, axis parallel line segments, then the square algorithm will not work. So what square algorithm you want to use? Let's say you want to use greedy algorithm, or so if you remember, okay, can you tell me which square algorithm you want to use, like greedy or shifted grid or quad tree? Which one? Because each of these has different problems. So if you have, let's say, shifted grid or quad tree kind of algorithm, what it does is it divides. It's either divide and conquer policy, but then it creates some kind of smaller cells, and it uses the property that if you have squares, then in this smaller cells, you can have only constant number of squares, and that you can solve in brute force way. But if you have arbitrary line segment, you can have arbitrary many line segment within the cells. So it will not extend to that case. So there are several technical difficulties if you want to extend the square algorithm even to arbitrary line, even to axis parallel line segments, because it's not generalized. The square is not a generalization of axis parallel line segment. It's a different case.
The volumetric argument won't work. Volume argument won't work, to just say that.
Yeah, exactly. The volume argument will not work. So for fat objects, we know that it has large volume, and that helps in these smaller grid cells, which does not work here.
So, okay then. So we end the session here. Thank you, Arindam,
Thanks a lot
for this wonderful talk. We will look forward to your next talk tomorrow. And thank you everyone for attending this.